Hi mathematicians. Today we're going to talk about Riemann sums and trapezoidal sums. In the last video, we learned what a Riemann sum is and how it approximates an integral. And we used rectangles to add up the areas to get an estimate of what the actual area would be. So if we have a curve like this, we drew rectangles to approximate the area under a curve. Now, instead of drawing rectangles, we can also draw trapezoids. A trapezoid has a base 1 and a base 2 and a straight line that connects them. So this is base 1 and base 2. And to find the area of this shape, the formula is A equals 1/2 base 1 plus base 2 times the height. This is similar to the formula base times height for a rectangle, but we're averaging the two bases since the height is not the same. So we draw our trapezoids instead of rectangles, where the two sides of the trapezoid are dictated by either endpoint. Let me draw one over here, where you might be able to see that difference. Here is the line that would connect them, base 1, base 2. You can see how a trapezoid might be better at approximating the area than rectangles would be, because it cuts off that extra space that we had here by creating a line between them. So let's do an example using a table and compare the midpoint versus a trapezoid. So rocket A has positive velocity, v of t, after being launched upward from an initial height of 0 feet at time t equals 0 seconds. The velocity of the rocket is recorded for selected values of t over the interval 0 to 80 seconds as shown in the table above. Using correct units, explain the meaning of the integral from 10 to 70 of v of t dt in terms of the rocket's flights. So let's look at the units. V of t is measured in feet per second. dt is measured in seconds. Time is seconds, velocity. I got my units from here. Remember, we're doing the base times the height. So if we multiply the base times the height, the seconds cancel, and the resulting units are feet. So that tells us we have something to do with position. And the integral helps us find the distance that we've traveled. So this is the distance traveled between t equals 10 seconds and t equals 70 seconds. So let's use a midpoint Riemann sum with 3 subintervals to approximate this value. So a Riemann sum with 3 subintervals. So I'm going to look at my endpoints, my boundaries, 10 to 70. That means the time is 60 seconds. 70 minus 10 is 60. And I'm dividing it by 3 for my 3 subintervals. So that gives me 20 seconds. And I'm starting at 10. So 10 until 20 seconds later is 30. Between 30, 20 seconds later is 50. And finally, 50 to 70. So we've divided into 3 sub-intervals. Now let's find the area for each of the rectangles using the midpoint. In the first rectangle, the base is 20. And for the height, we're going to use our middle value and find the velocity there, v of 20. Plus, for our second rectangle, the base is still 20, and we're going to use our midpoint, 40, v of 40 for the height. Finally, in our last interval, 20 is the base, the midpoint is 60, so we're doing it 20 times v of 60. I like to put v of 20, v of 40, v of 60, because if I accidentally make a mistake, they know what I meant to write, and I can get some points for this, even if I put the wrong value there. So now let's evaluate them. 20 times v of 20. V of 20 was 22. Plus 20 times v of 40 was 35. Plus 20 times v of 60 was 44. So if I add them all up, I get 2020. And my units are feet. Now let's use a trapezoidal sum with 4 subintervals of equal length to approximate the integral from 0 to 80 of v of t dt. Well, here, my boundaries are 80 and 0. So 80 minus 0 is 80. 4 subintervals, so divide by 4, and I still get 20. Notice in this one, I'm starting at 0. So starting at 0, 20 over, then I have 20 to 40, 40 to 60, and 60 to 80. Those are my 4 subintervals of equal length. So now we're going to use a trapezoidal sum. So for a trapezoid, the formula, remember, is A equals 1/2 base 1 plus base 2 times the height. So for our first trapezoid, we have 1/2. The first base, we're going to use 0. The second base, we're going to use 20. So v of 0 plus v of 20 times the height here is 20. Next, we're still going to have our 1/2. The first base we use is v of 20 plus, at the other end of this interval, we have v of 40 times your height, 20, plus in our next interval, the average, 1/2. Base 1 will be 40, base 2 is 60, v of 40 plus v of 60 times your height, which is 20, plus 1/2. Base 1 is 60 plus v of 80 times your height, which is 20. So notice here that all of them have this 1/2 and 20 because we made them equal lengths. They don't always have to be equal lengths, so make sure you check if it's equal lengths. But if it is, we can just factor it out. So this 1/2 times 20 is just factored out of all of them. So now we can just focus on the v of whatever we have. So v of 0 is 5, v of 20 is 22, plus v of 20 is 22, plus v of 40 is 35, plus v of 40 plus v of 60 is 44. And finally, we have v of 60 is 44, and v of 80 is 49. So we get our total is 2,560 feet. That's our approximation for the distance traveled between time t equals 0 seconds to t equals 80 seconds using a trapezoidal sum. Now let's do an example with an equation. Use the following methods with 3 subintervals of equal length to approximate the integral from 0 to 9 of x squared minus 2x dx. So let's do it using our midpoint Riemann sum. So if we have 3 subintervals, 9 minus 0 is 9. 9 divided by 3 is 3. So we're going to have from 0 to 9, 3 intervals, and it will be spaced every 3 numbers. So 0, 3, 6, 9. Now for the midpoint Riemann sum, we're going to want what is in the middle here. So between 0 and 3, 3 minus 0 is 3, divided by 2 is 1.5. So between 3 and 6, again, halfway is a distance of 1.5. So 3 plus 1.5 is 4.5. And finally, in the last interval, 6 plus 1.5 is 7.5. So I'm going to give this a name. I'm going to call it g of x. And for my midpoint Riemann sum, I know my base is 3, and my first midpoint is at 1.5. So times g of 1.5. For my second rectangle, the bottom of my rectangle is still 3, between 3 and 6. And I'm going to use the height at 4.5. So 3 times g of 4.5. Plus my last rectangle, the bottom is still 3, times the height is at 7.5. So to help me, we can use our calculator. In y equals, we put in our function. We can press trace, and we can type in the values we want to find. So for the first rectangle, we want to evaluate it at 1.5. So we press trace and type 1.5 and press enter. So we have 3 times, we're going to use our y value here, negative 0.75. To find the next one, we're going to type in 4.5. You can press trace again, but it will also work on its own. So we get plus 3 times 11.25. And finally, we plug in 7.5. Enter. We get 41.25. If we sum all of this up, we get 155.25. Let's compare that to a trapezoidal sum now. We're going to use the same intervals, 0, 3, 6, 9. But now we're going to use our trapezoidal rule. Now I'm going to use a quick shortcut to find our trapezoidal sum. As we saw in the previous question, each trapezoid had the 1/2. So I'm just going to pull out that 1/2. And each trapezoid also had the same height because it said equal length. Well, here it says equal length again, so I can pull that out as well. Now I just have to do the average of the bases for each interval. So I have the first set is g at 0 plus g at 3, using both endpoints to find the average of my bases, plus g at 3 plus g at 6. That's the two bases for the middle interval. Finally, plus g at 6 plus g at 9, which is the two bases for the last interval. So let's use our calculator again, although we could do it by hand in this case. So we put in our equation. Since these are all whole numbers, I can just use my table. Second graph. Pull out my 1/2 times 3 again. G of 0 is 0, plus g of 3 is 3, plus g of 3 is 3, g of 6 is 24, plus g of 6 is again 24, and g of 9 is 63. Simplifying this, we get 175.5. Finally, let's do a left Riemann sum. So this is back to rectangles using our same interval, the base of 3 times the height. If we're using the left in our first interval, we want g of 0. For our second one, the left side of the interval between 3 and 6 is 3. So 3 times g of 3. And the last interval, still bottom of the rectangle is 3. And the left side of this, between 6 and 9, is 6. Notice we're not using 9 at all because we're doing a left sum. If we were doing right Riemann sum, we wouldn't use 0 at all. So evaluating this, g at 0, well, we find that already is 0, plus 3, g at 3 was 3, plus 3 times g of 6, g of 6 was 24. We get 81. The actual value was 162. So you can see that the midpoint Riemann sum and the trapezoidal sum did much better than the left Riemann sum or the right Riemann sum would have done. In general, the midpoint and trapezoidal sums are more accurate than left and right Riemann sums. Also, the more subintervals we would have, we would be more accurate. I hope you enjoyed this video on Riemann sums and trapezoidal sums.